Hello, everyone. It's a special honor for me to join you today to talk about what I'm calling cities made of sky, the future of wood in the built environment. Today, I will talk about broad considerations regarding wood and wood technologies, especially for architecture and engineering. This first slide is a chart with some data here, so I will try to explain. There are two different trajectories depicted in this chart. Both trajectories illustrate a change in humanity's use of non-renewable resources and renewable resources. As we know, for the better part of human history, we as people have used wood and related biomass resources predominantly. But with the Industrial Revolution, everything changed. And despite the fact that wood was the primary material for architecture, engineering, and products, furniture, and fuel for so many centuries, sometimes people forget today because concrete and steel and plastics, other materials have become dominant. And so I'll talk about these two trajectories briefly for more information. The first, the upper trajectory that's in a red color, is from the engineer Michael Ashby from Cambridge. And in his research, he is illustrating the percentage difference, the proportional difference between reliance on renewable materials and non-renewable materials. And you can see in the detail here significant moments in time where the Industrial Revolution began, when concrete began to displace wood for those applications, where aluminum began to displace wood, etc. The other trajectory is focused exclusively on the United States, and it comes from David Morris, who is the director of the Institute of Local Self-Reliance, looking at what he calls the carbohydrate economy. And it's a similar trajectory in that, although the shape is different, the direction is the same in terms of the shift between what he calls minerals to vegetables, or really vice versa, from vegetables to minerals. All that is to say that until recent years, we as a human society have become almost exclusively reliant upon non-renewable resources. But the picture is changing, and it's changing very, very fast and shifting back towards renewable resources. We know this. This is both because we recognize the huge carbon benefits of using biomass in building and other applications. We also know this because non-renewable resources are limited. By definition, it's defined in the term non-renewable. And certainly there are repositories of oil or certain minerals, whatever resource you want to look at, that still remain, but by definition, those are less and less accessible, require more advanced technologies to access, more money, more development. So prospecting will continue. We will still continue to create products and buildings with steel, concrete, etc. But many resources, even sand today, are becoming scarcer, and there's concern about them. So those two forces are leading us to transition from a so-called hydrocarbon-based economy, or more broadly, a non-renewable resource economy, back towards a carbohydrate-based economy. This is a photograph that I took on a visit to Helsinki. I love this Chapel of Silence. It's so beautiful. And I love Finland. I'll share a quotation here from Harvey Green, who's written about the history of wood, just to talk about the kind of cultural attitude towards wood. So Green has said, quote, "For millennia, wood has been a familiar and ordinary substance, common in people's lives, used for heat, shelter, food preparation, light, tools, weapons, toys, storage, land and sea vehicles, decoration, and design. It is, in fact, so familiar that we often dismiss it as a common substance." But that's changing too. For us to dismiss wood as a common substance is unfair to begin with, because there are a lot more varieties of wood products and applications today than many people realize. But also, there are incredible advances happening with wood today. And I don't have to tell you that. You all know this reality, certainly with LVL. But many other types of technologies or applications using biomass and using wood today, which I'm calling not your grandparents' building material, and not to disparage our grandparents, but just to say that wood today is, I think, not recognizable from a couple of generations ago. And I would like to share, just for fun, I would like to share some incredible advances happening across the spectrum of wood technologies. One is this effort to advance capabilities to additively manufacture wood, so to 3D print wood, which is fascinating, especially because we're more used to 3D printing being used with plastics and some other materials like metals and ceramics, but wood. And so the technical term for this type of additive manufacturing is wood plastic composite based printing. Here's an example, an image that I took from a Future of Wood studio at the University of Arkansas. But there are researchers working around the world to explore this opportunity to work with wood in really fascinating new ways. Another recent set of technologies have to do with making wood insulation and foamed materials. This is a sample made from some of my students at the University of Minnesota who are repurposing wood pulp, paper pulp, this idea of reusing wood waste and new ways to have insulating value. There's a similar effort that's happened in more development started by the Fraunhofer Institute. Who would have thought that wood could be transparent? This is a technology developed by the Forest Products Lab at the United States, basically in the Forest Service. And this is a wood glass. I say that with finger quotes because it's not technically a glass, but it is a modified wood material to be used eventually for apertures. And this material outperforms window glass in many characteristics, including lightness, durability, and insulation value. We are increasingly interested in renewable energy, photovoltaics being a primary means of harvesting energy that's renewable. But we typically harvest sunlight power through silicon and other non-renewable materials as media. Why not mimic the function of photosynthesis even more directly by using materials from trees themselves? And so this is a development that creates, where researchers have created solar cells with nanocellulose substrate that's derived from trees. And one of my favorite recent advances is functionalized wood. This term functionalized is used more frequently in chemical engineering and related fields to talk about materials that have enhanced properties and enhanced capabilities. I'm generalizing there. In this case, researchers have been exploring, continue to explore, uses of wood that seem fascinating and perhaps even counterintuitive. We know that wood has an inherent insulating value, not inherently conductive, but researchers have been exploring the transformation of wood as a kind of nanoscience, as a nanoscience practice, into a conductive material. In this case, it's really a composite system. This is a flooring system that's developed to harness power from footfalls through a kind of triboelectric phenomenon. There are other versions of functionalized wood that can be used for conduit or cabling to actually convey electricity. And so all that is to say that there are fascinating things happening with wood today that we could not have imagined even just a generation ago, I think. Another significant topic, and perhaps the one that has become the most present in our minds, especially with the COP26 event currently happening, is climate change and wood and wood's capability to act as a carbon bank. I'm quoting here Bruce King, who's the author of The New Carbon Architecture, which focuses on wood and other biomass materials as being advantageous in construction. He says, quote, "For the first time in history, we can and should build pretty much anything out of carbon that we coaxed from the air." It's a perhaps painful reminder to know that concrete, steel, and aluminum, those three non-renewable materials alone, are responsible for nearly a quarter of total global emissions. And that most of these are used in the built environment. And something we also know, when we look at primary structure types and those materials, steel, concrete, and wood, and in this case, I'm comparing those three structures in a very generic way based on the same kind of carrying capacity, this kind of structural functionality. If you were to engineer a system to support a certain load, let's say. And when we do a life cycle analysis on these simple structural modules, we can see the relative impacts of these systems. And the different colors are the different phases of life: product, which includes processing, construction, and use and end of life. So we can see that much of steel's impact is in the product phase, and certainly much of concrete's due to the cement clinker's high embodied energy. Wood, of course, looks very favorable. There's still processing involved, right? There's still transportation involved, et cetera. However, there's this beyond life phase, so-called by the Athena Sustainable Materials Institute, but essentially the phase after life. What we're seeing here is the carbon sequestration impact, which is of positive benefit environmentally. So now when we apply this end of life impact, we still see in the green there that steel and concrete still require more carbon investment at the end of their life to recuperate materials. But with wood, it's negative in this case, meaning below zero. Of course, that's environmentally positive, that there's a net benefit. Just to reinforce that, I think we all know this, but I think begs or invites reinforcement that the CO2 that's the carbon that's stored in the wood makes it, in terms of the global warming potential life cycle assessment, better than when we started. Others have corroborated this data. The engineering firm Arup, for example, conducted a study of a multi-story building project they were designing in Portland, Oregon, with a concrete design versus a timber design. And you can see that over the life cycle, these two designs' performance diverged considerably. The concrete design, many more emissions, and the timber design actually had negative emissions or sequestration. You can see there's divergence based on the transportation distance. But that's the only major factor, and still with a long transportation distance, we still have a benefit. More recently, scientists at Yale and Potsdam Institute collaborated on a report that is a very ambitious study of what would this look like on a global scale. So it makes sense to very seriously consider timber in place of concrete or steel for primary structure and other materials in buildings. But what if we did this on a global scale? I'm quoting the article here to say that, and the article appeared in Nature Sustainability Journal. Might it be possible to transform buildings' potential threat to the global climate system into a powerful means to mitigate climate change? Here is a chart that looks at 4 different scenarios, from business as usual, what we do today, to using increasing amounts of timber in place of concrete and steel in all new building construction. This is a fascinating study because it looks at the whole world as a carbon bank through the medium of buildings and cities built with timber. Now, there are some significant implications here. To get from 10% timber towards 90% timber requires fundamental changes in our forestry resources. And obviously that we'd have to look at chains of custody and management very seriously, because at COP26, there's also legislation being suggested to limit deforestation, right? So we have to look at timber farming very seriously here. But the benefit, as you can see, the light blue bars are emissions, but then the white bars refer to steel and concrete emissions, that we can really reduce our overall emissions as we allocate more of building resources to timber materials. So this is the aspiration, and perhaps a question: is this the future? Will we build cities made of sky? And so just to conclude, Aaron McDade, who wrote an article in that Carbon Architecture book by Bruce King, says it very succinctly to capture the fact that the building sector comprises the largest, it's the most impactful single industry on global warming, with about 40% of resource utilization. So she says the building sector is a significant part of the climate change problem. But by that very definition, it must be a significant part of the climate change solution. And I find it fascinating and a welcome trend that the voices in the construction industry, manufacturers, contractors, architects, engineers, designers, are increasingly being listened to and looked to by these intergovernmental panels, climate change experts, scientists who are studying global warming, because they recognize if we're the biggest problem collectively, then we have the biggest possible advantage to gain by changing our practices. And I'm thrilled that you're having this conference, and I'm thrilled that you're getting together and collaborating to find ways that we can really all together be part of the climate change solution. Thank you very much.